Okay, thank you, Paul. Pleasure to see you, Nick, again. As Paul just told you, I'm Robert Kleinberg from Schlumberger Research in Cambridge, Massachusetts. And the title of my presentation is Storage and Transport of Hydrocarbons in Organic Rich Mudstones, which are in fact the shale that is discussed when we talk about the shale revolution. I'd just like to acknowledge that this work was performed as part of the Shale project, which is a collaboration between the MIT Department of Civil and Environmental Engineering, Shell Production Exploration and Shell Exploration and Production Company in Houston, and Schlumberger Research in Cambridge. And I'd particularly like to acknowledge my colleagues, Kirsten, Benoit, Roland, Franz, and Lederick. This is an outline of the very brief talk today in three parts. First, I'm going to be talking a little bit about the structure of organic rich mudstones, and particularly their porosity structure. The second part will be on Knudsen effects and geochromatography in the sub-nanometer pore population. And finally, I'm going to talk about the permeability inherent in the larger 10 to 100 nanometer pore space population. So first, let's look at sort of a typical mudstone, or shale as it's sometimes called, that is the source of all the oil and gas we use today, and in particular the oil and gas that we're getting directly out of these source rock environments. This is from the Haynesville Formation in northern Louisiana. You can see the 10 micron scale bar, and it's comprised of several elements. First, there's the inorganic grains represented by silica here, could also be calcite in other formations. There's also abundant amounts of clay represented here by illite, shown on various parts of the slide. There's pyrite, which is often found in conjunction with preserved organic matter because it's formed under reducing anoxic conditions, which are exactly the same conditions that promote the preservation of organic matter as it is deposited on seafloors and lake beds and then buried by normal sedimentation processes. So we often see pyrite together with organic matter. And the kerogen is the organic matter itself. And in this slide, it sort of comes in two flavors. There's a porous kerogen, which is shown circled in white at the bottom center of the slide. And then there's a kerogen that looks distinctly non-porous, except maybe for one big pore in the middle there. But the rest of it, at least at the scale of SEM, looks non-porous. Now, in reality, these rocks have three pore spaces. One is the inorganic pore space, which is mostly associated with the clay, which is generally hydrophilic, filled with water, and is thought not to promote transport of hydrocarbons. So that's a completely independent, interpenetrating pore space that, in essence, we don't have to worry about. The second is the porosity that we see in the frankly porous kerogen down here, as exemplified in the circle. And then the kerogen up here that looks non-porous at the scale of SEM actually has sub-nanometer pore spaces that we're going to be talking about first. So when we look using X-ray or neutron diffraction at these kerogens, what we find is invisible sub-nanometer pore spaces ranging up to, in this case, about 1 nanometer. Now, just to give you an idea of the scale of these pore spaces, a methane molecule, a single methane molecule, has a diameter of 0.3 of a nanometer. So these are really small pore spaces, and you might think that's kind of irrelevant. But in fact, an amazing amount of hydrocarbon can be stored in these sub-nanometer pore spaces, and that's exemplified by the molecular dynamics calculation shown on the right part of the slide, done at MIT, where the blue frame is the carbon backbone of the kerogen, which is mostly carbon, and the sort of red spheres are methane molecules. And you can see there's fairly high concentration of methane that can fit into these very, very small pore spaces. And interestingly, it's not just methane. Although the higher hydrocarbons, C2, C3, C4, and so on, all the way up as large as you like, are much bigger molecules, in their linear configuration, which is a very common type of subsurface hydrocarbon, as long as they're straight chain molecules, they can sort of slither through that pore space like snakes. And that's also illustrated in molecular dynamics calculations. So these substances can hold and also disgorge methane and even larger hydrocarbons. Now, however, the fact that the pore spaces are so small is a tip-off that hydrodynamic theory is not going to be adequate to describe the transport of these hydrocarbons in these nanoporous spaces. So what are we going to use? This graph basically shows the whole range of flow types in porous media, and it's parametrized on the horizontal axis by the Knudsen number, which is the ratio of the molecular mean free path, lambda, to the pore radius, r. And you can see when that ratio is small, in other words, when the mean free path is very small compared to the pore size, we're sort of very safely in the hydrodynamic regime, namely the flux over the hydrodynamic flux equals unity. As that parameter gets bigger, we get into what's called the slip flow regime, which is a simple correction to the hydrodynamic theory. And then at the far end, where the ratio is very large, we get into the ballistic regime of free molecular flow. Now, in between, there's a transition flow regime where the theory is very much more difficult, and that's where the MIT group has used molecular dynamics to understand how molecules can move in small pore space, in that intermediate sized pore space on this plot. I just want to say that the hydrodynamic regime at low Knudsen number is typically represented by what's called Darcy's law, which is a conductivity equation somewhat similar to Ohm's law, and it just assumes laminar flow in the pore spaces. So this is a plot which sort of is helpful for understanding where we are in that space of flow regimes. On the horizontal axis is the pressure in megapascal, vertical axis is the Knudsen number, that ratio of mean free path to pore size I just described. And the lines are parameters of basically pore size. So if you know your pressure, you know your pore size, you know what regime you're in. And so for that nanoporous and subnanoporous pore space in the kerogen, and for typical reservoir pressures, which are roughly between 10 and 100 megapascals, we are comfortably in or uncomfortably in this transition flow regime where none of the simple theories are going to be helpful. And that's where the molecular dynamics calculations really come into their own. So let's look at some of those calculations. This is a plot of adsorption on the vertical axis plotted against a pressure in megapascal on the horizontal axis. Both scales are logarithmic. And the lines are appropriate for various molecular species, starting with methane, which has 1 carbon atom, propane has 3, hexane has 6, nonane 9, and dodecane 12 carbon atoms. And these are represented as linear straight chain alkanes, which, like I say, is quite common in these reservoirs. And what we see is perhaps not too surprising qualitatively, that as the pressure increases, the adsorption of methane on that carbon structure increases. That's not surprising. And propane adsorbs more readily, not surprisingly, and so on. And of course, by the time we get to dodecane, it's basically adsorbed all the time. It's sort of stuck onto the walls. And that's all well and good. So these results gave us confidence that these calculations, which are based on fundamental principles, actually do sort of agree with our heuristics on how hydrocarbons should work in these carbonaceous pore spaces. Now, more interestingly, the flux of these various hydrocarbon species was calculated as a function of pressure gradient on the horizontal axis, flux on the vertical axis. And in this case, methane, which is shown in red, is the topmost line, and then they move down through the propane, hexane, nonane, and dodecane. Now, this is, at least again, qualitatively not surprising because we know from laminar flow theory, hydrodynamic theory, that flux should decrease as viscosity increases. So is this a viscosity increase effect? That's the first question you ask. And the answer is no. What we do is we sort of divide out viscosity from the problem. We know those values are handbook values. And we plot permeability. Now, permeability is the ability of a solid frame to transmit fluids under pressure gradient, and it's a property of the frame alone. So basically, all the fluid effects have been taken out. They're encoded in the viscosity. So now when we look at the apparent permeability of this nanoporous kerogen model for methane at 150 degrees C, again, typical reservoir condition, we see that the apparent permeability is not independent of hydrostatic pressure like it should be. If this were in the hydrodynamic regime, the hydrostatic pressure, which changes the fluid properties of the methane, would have no effect on the properties of the frame, which is the permeability. So we know that we are not in the hydrodynamic regime. On the other hand, when we look at the permeability versus adsorption, as calculated 2 slides ago, you see that there's a very nice inverse correlation between them. And on this plot, I've included methane at various pressures along with hydrocarbons at 25 megapascals, all at 150 degrees centigrade. And you have this very nice inverse relationship, which suggests that we are not in the hydrodynamic regime, but we are dealing with what we call geochromatography, which is the ability of substances to flow through solids where there's an absorption going on, just like a regular gas chromatograph column. So let's go back to our picture of kerogen once again, and this time we're going to focus on the more porous kind of kerogen down here in the white circle. And again, these pore spaces are in the 10 to 100 nanometer pore size, and when we look at them on our handy chart, we see that we are generally, under reservoir conditions, we are generally safely within the Darcy flow or hydrodynamic regime, perhaps with some contribution of that simple slip flow correction. So when we measure permeability in the lab, which we generally do by taking a chunk of rock, cutting it into a cylinder, right, circular cylinder, and applying a pressure gradient and measuring the flux, I can assure you that will be dominated by the largest end-to-end flow paths, namely that those 10 to 100 nanometer that we see in the scanning electron microscope and by other means. And that it's not going to be affected by the sub-nanoporous, those pore spaces are simply too small to transmit fluid. On the other hand, when we ask the rock, how are you going to produce oil and gas? Well, it's all stored in those very, very tiny sub-nanometer pore spaces. It will flow out, not hydrodynamically, but according to the Knudsen, and into 100 nanometer flow channels, which would then take it out to perhaps microcracks and then to the hydraulic fracture system. So we are presently coding up that scheme to put into reservoir simulators to more accurately predict how fast oil and gas will be produced from reservoirs. So that concludes my presentation. This is the picture of a Schlumberger frac spread. As you see, the rocks and pores may be small, but the equipment's large, and now we'll take some questions.
Thank you, Bob.
Yes.
I have 2 questions. First question is that you make a comment about the water wetting, clean minerals, but do you think that the kerogen phase will make a continuous flow path, or they have to pass through some such water wetting phase to overcome large capillary pressure? So that's the first question. Second question is for the molecular dynamic computation. Do you think up to what pore size will you will not see geochromatographic effect? Because your simulation shows that 1.2 nanometers.
Yeah, okay. There were 2 questions. The first one was the water-wet flow system that is dominated by inorganic minerals, what effect will that have? And as the questioner pointed out, there's a large capillary pressure block for hydrocarbon to penetrate that flow system. I mean, it's an enormous capillary pressure block. As you can perceive with those, even the 10 to 100 nanometer pore spaces, very much, I mean, this would be considered a cap rock in an ordinary oil and gas reservoir. So, although I have no direct evidence, I would say it's highly unlikely that that's going to be a meaningful flow path for organic molecules. And I think that the flow is almost totally through the organic pore space and perhaps microfractures and microcracks in the rock, which give you a bigger pore space to allow the hydrocarbon to get by, perhaps water that might be there. The second question was, let's see, that was the, what size do we need to, what's the minimum size that we need to worry about molecular dynamics calculations? Yeah, okay. Well, that's where the hydrodynamic theory is going to work, and that's in, as shown on this slide, that's sort of in the, at reservoir conditions, the 10 to 100 nanometers, hydrodynamic theory works pretty well, and molecular dynamics should no longer be required. That's what this tells me.
Okay, thank you, Bob.
Okay.
We're going to move on to the second.